Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome, everyone. Thanks for coming. It's my pleasure to introduce Anirudh Badam, who's here today from Princeton, and he'll be telling us about how to use SSDs and other sundry devices to bridge the gap between memory and storage. And just in case you don't find that interesting enough, when you get a chance to talk to him, he also enjoys rock climbing and reading books about modern physics. So feel free to question him ruthlessly on those topics as well. Thanks a lot, and go ahead.
Thanks for the introduction, Jeremy. I'm Anirudh Badam. I'm from Princeton University, and I'm going to be talking about bridging the gap between memory and storage today. So the motivation behind the talk is that over the last 2 or 3 decades, the capacity and performance gap of memory and storage are increasing. These gaps are in terms of not only in terms of IOPS per second, random IOPS per second, but they're also in terms of capacity. So if you look at state-of-the-art memory units today, they can do anywhere between 1 million or 1.5 million IOPS per second. And if you look at state-of-the-art disks, they can do between 100 to 300 seeks per second. There are some that do slightly higher as well. And with respect to capacity, you probably can get somewhere between 200 to 300 gigs of DRAM on a per rack unit basis today. And that's the maximum that you can get. I mean, there are capacity constraints for really high density DRAM. It's essentially not only the logic board needs to be capable enough to have high density DRAM, but the high density DRAM is also expensive and does not scale beyond a certain point at every point of time. This 8 terabyte of disk per rack unit is probably conservative, but you can get as much as maybe 20 terabytes of disk inside a single rack unit today of magnetic hard drives. So the big question is, how do you bridge these gaps? I mean, for applications that have some IOPS requirement between these two, but capacity requirement also between these two, how do you bridge these performance and capacity gaps? So this talk focuses on helping network appliance caches bridge this gap. Network appliance caches like web-proxy caches, like HTTP caches, which cache static objects, and then network accelerators, which have the capability of caching dynamic content based on content fingerprinting, and inline data duplicators, which are essentially trying to index all the data that you're trying to deduplicate and try to do inline data deduplication before you store certain things on the disk, and also file system and database caches. And this talk essentially is trying to help these systems scale up by using software and hardware techniques. So the first technique that I'm going to talk about today is called HashCache. It was presented at NSDI 2009, and it's going to be a purely DRAM and disk talk. It's about reorganizing your data structures such that you can bridge the capacity gap between DRAM and disk. The second talk is going to be about using alternative memory technologies, which neither have the performance bottlenecks, neither the capacity bottlenecks of these two technologies, and fall somewhere in between, and try to find the right way of using these technologies to bridge these gaps for network appliances. So this was called SSDAlloc and was published in NSDI 2011. So before delving into the talk, I'd like to give a brief introduction of how caching works, because that's the system that we're going to focus on. So let's say there are 3 systems that are trying to talk to a server, and these 3 systems are essentially interested in some content. That content is showed as a red blob over there, and these 3 clients are essentially fetching the content from the server individually. That sort of increases the network traffic if these clients are co-located, and the server that they're talking to is the same one, and the content is the same one. So the way in which you solve this problem is introduce a box that is nearer to the clients, a smaller one, and this box essentially downloads the content that is interesting to all the 3 clients once, and the clients individually fetch the content from the box that is nearby. So this decreases the traffic on the wide area link, and also decreases the latency for the clients for accessing the content. So here's an architectural overview of how people build caches. There's a cache logic, cache application logic that multiplexes between client connections and server connections, and fetches content from the server and serves it to the client. And it essentially architects its memory into 2 different parts. One is the cache index, and the other is the block cache, which is the data cache that it can cache in memory as much as possible. And the cache index essentially is used to serve membership queries. So if a particular object belongs to cache, is currently cached, it fetches it from the cache and serves the query. And if it's not currently in cache, it fetches it from the network, stores it locally on the storage, and then continues the operation from there on. Now this was a problem that was well studied during the 1995-2000 period. So why consider reopening it, right? So the reason behind why this problem is important again is that disk capacity is outpacing memory capacity, as I said in the beginning of the talk. This means that there is a problem of the cache index overflowing onto the disk itself and reducing the performance of these systems. So I'll talk more in detail about what these trends are with respect to disk capacity increasing beyond memory capacity, and point out how this actually leads to problems for cache indexes. So if you look at varying different disk properties from over the last 32 years, how they have changed. The largest disk that you could have obtained in 1980 was 80 megabytes in size. And today you can get a single platter 3 terabyte hard drive. And this is about 100,000 times better. And it's almost twice increase every 2 years. I mean, if you look at the last 32 years. But the seek latency unfortunately increased only by 2.5 times. And I mean, the seek latency directly translates also into the number of seeks that you can do. So the IOPS haven't gotten better, but the capacity has certainly gotten better for disks. So this rapid increase in capacity means that larger indexes are needed to be able to index all these disks. And the bad seek latency means that the index cannot overflow to disk, because if the index overflows to disk, you're essentially reducing the IOPS, the performance of the system itself, because now you would be using a seek for cache lookup and also one for serving the actual request. The obvious question is, I mean, why do you need these big caches? I mean, why do you need a 3 terabyte cache, right? So if you look at how data has been growing, there's this survey done by Cisco last year among its customers who are using its routers, and they've found out that raw unstructured data like email, documents, and photos has been increasing by 40 to 60% every year. And this means that the number of objects that need to be stored, that need to be cached, is also increasing every year. And data is also being accessed more. There is this new informal law called the Zuckerberg's law, which states that the number of pictures being viewed on Facebook is doubling every 18 months, which means that people are not just creating this data, but they're also accessing more of this data more frequently. So it's not just that they're putting it to disk and never accessing it. So the performance is actually important for these systems. So there's a reason why index operations might be fast. You need to be able to find out membership queries whether a certain thing belongs to a storage system really fast. And the third problem, the third trend in terms of DRAM price limitations and DRAM capacity limitations that is causing indexing problems is the following. So this is data from 2011. If you look at the price of a server and vary the amount of DRAM in a server, the cheapest 64 gigabyte, the cheapest server that you can get with 64 gigabyte DRAM is probably not more than $1,000. But the cheapest server that you can get as a single system image with 2 terabytes of DRAM is actually about $250,000, and the increase is actually super linear, and not just in terms of initial cost, but also in total cost of ownership, because high density DRAM actually increases super linearly in cost, and the logic boards necessary for being able to have higher density DRAM in your system are also more expensive on a single system image basis. So once we have all these bottlenecks, the question is, can we improve indexing efficiency? So we have DRAM bottlenecks, we have data itself is increasing, and we also have disk trends that are problematic. So the first system, as I said, is going to be a purely DRAM and disk talk, which is trying to address these growing gaps and trying to reduce the size of the indexes itself, so that with a limited amount of DRAM, with just a few kilobytes or megabytes of DRAM, you can index terabytes of hard drive. So these are the high-level goals for HashCache. Interface-wise, it looks like a simple key-value cache. Your keys and values can be of varying lengths, and it also needs to have a good cache replacement policy. For any cache, the better the replacement policy, the better the hit rate, which means the better the performance is going to be. So those are the requirements from an interface perspective. From the perspective of solving the problem itself that I'm talking about, we need to reduce indexing overhead. As I said, we need to answer the question of is it actually possible to index terabytes of storage with a few kilobytes or megabytes of DRAM. And is it also possible to trade memory for speed, which means that the more memory you add to index, the higher the performance should be. Is that such indexes are such indexes possible? Is the question that we are asking in HashCache. So before delving into what HashCache actually is, I'm going to give you a brief overview of how people actually build LRU caches today. So various functionalities are there in LRU caches. One is existence identification. You need to be able to tell if a certain element belongs to a cache. People build hash tables with chaining pointers and hash value to figure out if something belongs to the cache. And for implementing a replacement policy, they have LRU pointers across the entire data set that they have. And the location information is the place on the storage, the location on the storage where the actual object resides. And there's other metadata information that is related to the objects themselves. So I'm going to be talking about two systems as points of comparison. One is a popular open source caching system called Squid that has about 66 bytes per object requirement for creating an index. Bulk of this actually goes into a 20-byte hash value that they store. And the 20-byte hash value itself is actually used for creating a storage location on the file system. So they don't have a specific requirement for storage location itself. And commercial systems try to improve on this. They store a much smaller hash value in memory as opposed to storing a large hash value. And they resolve collisions on the storage itself. And the memory requirement comes down to about 24 bytes per object. So in HashCache, we try to rethink the cache indexing itself. The requirement, as I said, indexes that require very little amount of memory to index large storage, and we redesign memory and storage data structures for network appliance caches for this purpose. As I said, it's an in-memory index that can be used for network appliance caches like HTTP caches and WAN accelerators. It's about 6 to 20 times more DRAM efficient than state-of-the-art indexes with good replacement policies. And it was selected as one of the top 10 emerging technologies of 2009 by MIT Technology Review magazine. And the approach of HashCache is the following. The bulk of the memory usage in these systems actually goes into storing pointers for implementing hash table chain collision, and pointers also for implementing least recently used replacement policies. So the approach inside HashCache is to try to get both of these things, collision control and replacement policy, without actually using any pointers. So here's an overview of the HashCache techniques. There are 8 policies that are there in the paper. I'm going to be talking about 3 policies in the talk, but 4 of these policies are actually given. The y-axis is the indexing efficiency. That is essentially, you could think of it as how efficiently they are using DRAM, and the x-axis is performance. So as you can see, there are varying policies of HashCache that can actually match the performance of open source system at 10 times and at the same time are 10 times more memory efficient. And there are also versions of HashCache which are actually 5 times more memory efficient than state-of-the-art commercial systems, but still be able to match the performance. Please.
So is the units for index efficiency the reciprocal of the bytes per object stored that you showed on the previous slide?
It's given in terms of dollars per. It's given in terms of number of index entries that you can store per dollar.
So that's equivalent to the thing. Is that equivalent to the thing I said, or did I miss a?
That's equivalent.
So can I read that factor of 10 to mean that you're storing 6.6 bytes per indexed object?
No, I mean the 10 times more is essentially for a given amount of DRAM, HashCache can actually store 10 times more entries.
Okay.
So that means that the disk that you can index can be 10 times larger for a given amount of DRAM.
10 times more objects, or 10 times?
10 times more objects, and.
Okay.
The two aren't equivalent. Adding more disk space is very different from adding a large number of objects.
Sure, I mean, it depends on the object size distribution.
Caching 100 million 1K objects is a much harder problem than caching 100 million 10 meg objects.
Absolutely. So I'll talk about varying object distribution sizes. And the first part of the talk is going to be about object distributions, which are essentially HTTP based. And the second part of the talk is going to talk about object size distributions, which are more conducive to network acceleration and essentially network content fingerprinting, and also for storage content fingerprinting, useful for deduplicators. So here's the first HashCache basic policy that essentially talks about how to build these indexes. Let's say you have a URL, and the data corresponding to this URL is these 4 blocks of green data that I've shown you. What HashCache does is it takes h bit hash value of the URL. It uses some hash function to obtain h bits, and it uses a part of the storage system as an on-disk hash table. What it does, it takes n contiguous blocks on the magnetic hard drive and uses it as a hash table. What it does is it takes modulo n of the hash value that you have and obtains a value t. Let's say on the tth block on this on-disk hash table, it stores the first block of the data. And as I said, HashCache has a requirement of varying sizes for objects. The question naturally is, where do you put the rest of the data? If all the objects were of same size, you could have essentially had all your disk as a single large hash table. So what HashCache does is it uses a large portion of the magnetic hard drive as a circular log and stores the remaining part of the data in the circular log. And the first block, the hash table, the n contiguous blocks hash table that we call as the disk table, stores a pointer to the log where the remaining data is actually stored. So, and as you noticed, this requires no bits per entry in the DRAM, because the hash function that you have can be represented in constant number of bits that you can store in DRAM, and it does not have any DRAM requirement for storing, because you just get the hash value and you're using the disk as a hash table. The advantages, as I said, is that are no index memory requirements, and it's tuned for one seek for most objects. If you design your on-disk hash table with a bin size of so and so, let's say 70% of the objects are smaller than the bin size of your hash table, which means that 70% of the objects can now be accessed in one seek on the disk. The disadvantages are, it's actually one seek per miss, which means that misses for any cache are not going to increase your performance. They're just a nuisance and increase the latency, not useful for your application performance. And this sort of a system which is using disk as a hash table would be wasting a seek on a miss, and it's essentially increasing the application performance in all scenarios, not just hits. And there's also no collision control. The collision control is implicit in the sense that if you have two URLs having the same hash value, they'd be replacing each other. And there's also no cache replacement policy. The cache replacement policy is also implicit in terms of hash collisions. So I suggest the following improvements. The first improvement that we suggest to this technique is collision control. What we do is, instead of using a simple hash table, we use a set associative hash table on the disk, and we call this, let's say the set associativity is T-way, and T is a configurable value in HashCache. That's the first optimization to this basic policy. The second one is we would like to avoid seeks for misses, and for this purpose what we do is we store a small low false positive hash value of each URL in DRAM itself. Now the location inside the hash table itself gives you a lot of bits about the hash value itself, so you don't need to store all the hash bits. You only need to store a very small number of bits, because the location inside the set associative hash table already gives you a fair number of bits of the hash value. And third thing we do is we add a replacement policy, and we add an LRU-like replacement policy. What we do is we do LRU within each set of size t, and for representing the rank of the LRU rank of each element in the t size set, we only need log t bits as opposed to an 8-byte pointer for representing global LRU information. Now this means that the replacement policy is not global, but is local to each particular set. And I'll talk about how local LRU replacement policies work well in practice when you have varying different kinds of cache hit rates. So here's a graphical representation of how this HashCache policy called SetMem works in practice. You have the same set of input, the data and the URL of 4 blocks. You hash the data, and you take modulo the number of sets that you have in your hash table, and you get a value t. As I said, there are 2 hash tables now. One an in-memory hash table that stores the hash values, and one an on-disk hash table that stores the first block of the data. So in the tth set, in the in-memory hash table, what you store is you store a low false positive hash, and you also store the rank bits. The rank bits represent the LRU rank information of each element within this set that you have. Those are stored in the tth set in the in-memory hash table. The first block of data is stored on the in-memory on-disk hash table, and the rest of the data goes onto the log, like in HashCache basic policy, and the on-disk hash table stores a pointer to the log. And as I said, the LRU is now within set as opposed to being a global LRU policy. In practice, we needed 11 bits per entry for implementing this implementing this caching policy. The advantages of this are that no seeks for most misses. Most misses can be answered using the low false positive hash value that you have. If the hash does not exist in memory, you need not go to the disk. It is optimized for one seek per read, which are hits, and one seek per write, which is essentially you take a miss, go fetch the content from the network, and you want to cache that object right now, and that's a write in your cache. And it's a good hash and replacement policy in just 11 bits. There's a disadvantage is that writes still need seek. So if you look at any sort of system that tries to optimize operations for magnetic disks, you would like to coalesce all your writes and write them at the end of the lock, essentially trying to maintain the disk as a lock structured system. That means that most of your random seeks are going to be used for reads as opposed to being used for writes. So we propose the following improvements to HashCache. The first thing we do is avoid seeks for writes. Write everything in a log and eliminate the disk table. There's no on-disk hash table. The natural question is, where does the pointer go? Pointer into the log. The log location is actually stored in memory itself. This is not a pointer. This is not a pointer in. This is not like a regular in-memory pointer. It's a pointer to the storage location. So it's essentially the location information. The second optimization we try to do is avoid seeks for related objects. Let's say one of you goes to the main page of Microsoft and fetches the web page, and then let's say second person goes to the main page of Microsoft and fetches the content. Now the first person who downloaded the content would be doing a lot of random seeks and fetching all the content. There's no reason why the second person should also go and perform all these random seeks. If there are objects that are on the Microsoft page that are related to each other that will be used at the same time, then it makes more sense in storing them contiguously on the disk. So we do this optimization as well. Whenever you fetch content that are whenever you use content or fetch content that are related, that the application can actually express, saying that this content is related and will be accessed together, you actually store the data contiguously on disk. And that's also an optimization that HashCache supports. So here's the graphical representation of HashCache log policy that you have. Take the hash value, you take the modulo the number of sets of the hash value, and you get the value t. There's only in-memory hash table, there's no on-disk hash table. The on-disk data structure is a simple log, and the LRU is within the set. The first, in the teeth set in the in-memory hash table, what you store is you store a low false positive hash, you store the rank bits necessary for representing LRU information, and you also store the location bits. The location bits essentially are the pointer to the location in the log where the data is stored. So in implementation, we needed about 43 bits per entry for implementing this HashCache log policy. We now move on to evaluation. For evaluating HashCache, we used a system called Web Polygraph. It's a de facto testing tool for web proxies. They test hit rate, they test latency, and transactions per second of a given cache, of a given size, and of a given hit rate. And we tested all these policies.
Before, in the previous slide, you were saying you use the hash value, you look in memory table where it's stored on disk. Isn't that essentially haven't we gone back to having a hash table in memory for?
Sure, but instead of having pointers for storing LRU information and for chaining pointers, we don't have any pointer requirement, which means that the per entry overhead is quite low, and the original point that adding more memory should lead to higher performance actually translates. So HashCache basic does not have any memory requirement, but its performance is really low because it uses seeks for misses. HashCache SetMem on the other hand stores a very small false positive hash value in memory, gets you slightly higher performance. HashCache log gets you best performance but uses the most amount of memory. So it gets you that trade-off in terms of memory requirement versus performance. But all three are dramatically more memory efficient than state-of-the-art open source and commercial systems, almost 6 to 20 times. And we compare all variants of HashCache with Squid and Tiger, which are open source and commercial systems respectively. Tiger was is a proxy of a commercially deployed commercial CDN that is in use today. And our test box is a 2 GHz CPU, 4 GB of DRAM, and 5 90 GB hard drives. The paper actually tests hard drives as large as 4 terabytes as well. But here I wanted to show the performance implications of using multiple disks and trying to get as many IOPS as possible inside a single HashCache system. So this is how the indexing efficiency of HashCache looks. The x-axis is essentially the size of the largest disk that can be indexed using a gigabyte of memory for various caching techniques. Open source and commercial are barely able to index a 100 gigabyte hard drive using 1 gigabyte of DRAM. HashCache Basic can potentially index infinite amounts of disk because it does not have memory requirements on a per entry basis. And HashCache Log indexes about 1.5 terabytes of hard drive, and HashCache SetMem about 6 terabytes of hard drive for a single gigabyte of DRAM.
This is assuming some standard object distribution size.
Right. So the object distribution size comes from Web Polygraph, which was used by commercial proxy sellers using during the 2000 period, and they were getting their distributions from proxies that were deployed across many Blue Coat and Cisco systems.
And do you have some sense for, in today's web, how much increase in hit rate you get from indexing a larger disk? Because if you're in the heavy tail part, then
absolutely
doubling the size of the cache will only increase the hit rate by 5%
right.
or something.
So we originally started this this project trying to see if you can provide offline Wikipedia sort of systems to countries like Africa and India. And in that setting, I mean, offline sort of removes the scope of the involvement of the user. So that's when we thought, okay, the right match would be something which can have large amount of content offline, but also have some amount of participation as well. So that's when we thought large caches actually makes a lot of sense in those sort of settings. And we actually went and deployed some of these systems in Africa as well, where we populated it with a large number of Wikipedia entries. But it also not only serves as a cache, but also serves as an offline Wikipedia and offline encyclopedia sort of a thing. So in those scenarios, it is useful. And the second scenario in which it is useful is this is for static content. So you see this heavy tail in terms of for static content. And when the content itself is increasing in size, and you want to do content fingerprinting based caching, where you want to do dynamic caching, be it of storage or for network acceleration, you actually see higher benefits. So there's this IMC paper by my group made last year, where he mined the logs of the system called Codeine that my advisor has. It's a wide area CDN deployed on top of Planet Lab. He did some experiments of what happens when you do content based caching as opposed to static HTTP caching, and he saw that as the disk size increased from 1 terabytes to 2 terabytes, the hit rate actually increased from 16 to 27%. So you don't see that long tail in terms of dynamic content, and static content definitely yes. But the application scenario originally was these for the offline Wikipedia setting of developing regions.
So if I understood you right, for the web polygraph thing, those object sizes and distributions were based on research done in 2000?
Right. Right.
So
and
web has changed insanely in the past 10 years.
Absolutely. I'm going to come to the next system which actually does which actually takes the characteristics of the modern web. This was also an IMC paper last year by a group mate of mine, and where he shows the difference between how web changed from the web 1.0 days, and how object size distributions have changed, and how it actually affects the performance of these sort of systems. So in terms of memory usage, here is what HashCache does. With just 80 megabytes of memory, it provides it is about 5 times more memory efficient than state-of-the-art commercial system, and is still able to perform well, still able to compare in terms of performance. And there's also a version of HashCache which is probably 80 times more efficient than an open source system, and still be able to perform comparatively over there. So the normalization of memory requirement is in terms of the highest performing HashCache requirement, which is 1x, and the memory requirements are shown in terms of the memory requirements of HashCache SetMem, HashCache log over there.
So as I look at this, you're giving measurement in performance from requests per second per disk, but I haven't seen how you handle multiple disks.
So we simply stripe blocks across multiple disks because because it essentially is a hash-based index. You can do some sort of trivial load balancing across multiple disks, or you can even stripe blocks across multiple disks and try to get performance in parallel as well. So we've had some deployments in Africa. So we still have a deployment going on in Uganda, and these are the photographs from those deployments. So the question is how scalable this model right? I mean, in terms of if you have just a purely DRAM and disk-based system, you optimize your data structures so that you can bridge these gaps. I mean, for how many applications can you do this, and is it even possible to do it for all the applications? When do you sort of run into the actual limitations for an application in terms of you need more DRAM for performance, sort of a thing. So one scenario in which this can happen is where the object sizes are much smaller, and even with a very nice technique like HashCache, you do not have enough DRAM to store all the index. If your object sizes are, let's say, 128 bytes or 256 bytes, if you're doing aggressive network caching or aggressive deduplication for your storage system, this could happen, like very small object sizes. And for these scenarios, you still need indexes that could be much larger than the index that you have. So as I said, I mean, there are these disk properties that have gotten better, but there also, if you look at how much time you actually need to exhaust the entire disk by using random seeks, it used to take 600 seconds back in 1980. So reading 30 megabytes using random seeks of 8 kilobytes each takes 600 seconds. But now it takes 270 days, almost 3/4 of a year, right? So what this means is that even though capacity has increased, random seeks not so much. So this is 40,000 times worse today. So, and this scenario actually does not go away if you use faster disks. Even if you have 15,000 RPM disks, you probably only get twice as many random seeks per second. And the capacity, there's also a flip side of using a faster disk, is that the largest capacity disk that you can get for a higher speed spindle is also much smaller, because it needs to, it's a mechanical device and it can only do so much, the motor. So I'd like to reproduce this graph from the beginning of the talk, where there's super linear increase in terms of cost of having more amount of DRAM in a single system image. But there's a nice price point here. There's new memory technology, flash memory. If you look at high-speed flash memory devices like Fusion IO, you can get a 10 terabyte SSD today for the price point that you won't even get even a single terabyte of DRAM in a single rack inside a single system image. So the second part of this talk is going to be about new memory technologies like flash. And here's a small primer of flash memory. You can get about $10 a gigabyte, but if you're doing bulk, probably can get $5 to $8 as well. And it's about 1 million seeks per second per PCI bus that you have. If you have multiple buses in the system with like a NUMA machine, the IOPS actually scales with the number of buses that you have. And it's also very high density. You can fit as much as 20 terabytes of NAND-Flash in a single rack unit. And this actually also scales with the number of buses that you have. So the more buses you have, more PCI slots you have, the more 20 terabyte hard drives you can have in a single rack unit. And the advantage is that there's no seek latency, only read and write latency. And there's also a flip side which makes things more interesting, I guess. Writes happen after an erase, and these erases are usually 128 kilobyte blocks. And the number of erases that you can do is also limited in terms of let's say you could probably only do 10,000 erases per second of today's state-of-the-art NAND-Flash devices. So reducing the number of writes helps, and reducing with performance and also with the reliability of the device. So if you want the device to last longer, you would want to do as little of these erases as possible. So now the question of is, now that you have this technology which falls in terms of performance and capacity in between these two technologies, how do you want to use it? You want to use it as a fast disk, or you want to use it as a slow memory? So this is a simple experiment that we did. We took MySQL InnoDB, and in MySQL and a box, the first the bar over there shows you performance of what happens with TPCC when you don't have any flash in the system. Okay, that is normalized to performance 1. Okay, let's say you add some amount of flash into the system and you use it as a transparent block cache for the magnetic hard drive, and you run the TPCC benchmark on MySQL InnoDB. No source code is modified. You get about 60% performance improvement, 55 to 60% performance improvement. Right? Now you take the same system, instead of using the NAND-Flash device as a transparent block cache for the magnetic hard drive, if you use it as slow memory, as you configure it to use, you configure MySQL to use the flash memory device as buffer pool, you get a much higher performance. So this is very surprising. In either of the cases, there's no source code modified. In one case, you are using it as disk, and in one case, you are using it as memory. The reason this happens is the data structures that you build for memory are more flash aware in general, and the kind of optimization that were done for the disk world do not apply for flash memory, and they add some latency in terms of software, and that leads to these overhead in terms of using flash as slow disk as opposed to using it as fast memory. So that's the reason why my proposal is to use flash as slow memory as opposed to using them as fast disks. So if you look at state of the art in terms of how one could use a flash memory disk as memory, is use it as a swap disk inside, or mmap a file on the device, and there you go, it's available via virtual memory, the flash memory device. The advantage is that applications which are using malloc or mmap need not be modified. They can suddenly have large amount of memory that is flash backed. It does not, but the disadvantage is that it does not address SSD's problems. It's not flash aware, it does not do any write optimizations, and it might as well do a lot of random writes, because random writes are not a problem with respect to virtual memory or traditional physical memory technology, which is DRAM. So to address these bottlenecks, to address these issues, what people usually do is they rewrite their application. They optimize their applications for writes on top of flash memory, and the disadvantage is that you not only need application expertise, but you also need SSD expertise, right? You're modifying the application to be more flash aware and flash friendly. So the premise behind SSDAlloc is, can we get best of both worlds? That is, application need not be modified, or in the that's the ideal case. But is there a case with the number of modifications to the applications are minimized, but you're still optimizing for writes? So this is the premise behind SSDAlloc, and we try to solve this problem. So we started off with a simple approach, a non-transparent approach. What we did was we created a custom object store on top of a flash memory device, which is a log-structured object store. And the log-structured object store essentially gives you custom pointers to create, use, read, and write to from these objects that you're creating on top of the SSD. And you read and write objects as necessary. As I said, SSD is managed as a log-structured object store. It not only minimizes the number of erasers that you have on the SSD, but also optimizes for writes, because the writes are now done to objects as opposed to being done to blocks or pages like virtual memory systems do. But the disadvantage of this approach is that it still needs heavy modifications. You need to know where the objects are there in your system. You need to appropriately read them in and write them to from the SSD. And for example, HashCache, when we tried to convert HashCache to this particular object store sort of a model where we were storing each set inside HashCache as an object on the SSD, we needed about 500 lines of code to be modified inside HashCache. Now that was about 5% of the entire HashCache, just the indexing part, not the HTTP proxy part. Now this is a fairly large number of lines of code. Now, I built HashCache myself, so it was easy for me. But for someone who's not familiar with the application, and for someone who's not familiar with the SSD, it might take much longer and it might be much harder. So that's when we thought of this technique of, can we use the virtual memory hardware? Can we use pointers themselves to figure out what objects are being read to and what objects are being read from? Can we use virtual memory addresses as the object handlers? That's when we had this idea. So you could use page faults to detect reads and writes about which data is being read in a system. And on fault, you materialize the data from the SSD and manufacture a page. And you remove idle objects to the SSD's log, right? But the problem is that pages are 4 KB in size. Virtual memory systems, any modern virtual memory system does not give you access information of anywhere less than 4 kilobytes. There were systems which were doing this for 1 kilobyte and much smaller in size, but they do not exist anymore. And all the x86 systems, the smallest page size that you can configure is 4 kilobytes. And so then we had this wild idea of aligning objects to page boundaries. So instead of having contiguous virtual memory allocations, why not give each page to each object, and the virtual memory system itself will tell you which page is being modified. And if you have this model called one object per page, you know precisely which object is being modified. Now the rationale behind this crazy idea is that virtual memory is cheap, right? So you have 48 bits of virtual memory space, and this is much larger than the physical memory that you have in a system. But physical memory is not cheap. So you still need to you still need to build a system such that even though there is frivolous use of virtual memory, there's no wastage of physical memory. So that's the technique in SSDAlloc.
Virtual memory is not that cheap either. I'm wondering what one object per page does to your TLB.
Absolutely. So the premise behind SSDAlloc is for improving the performance of network appliance caches. So the network appliance caches are usually bottlenecked by the network latency and other aspects as opposed to just being CPU bottlenecked. So for these sort of systems, let's say you create all your objects. Let's say we are talking about something like Memcache. Inside Memcache, you have a hash table, which have a lot of values. If you create your values using SSDAlloc and you create your hash table using malloc, the good thing about SSDAlloc is that it coexists with malloc. So if you have some way of configuring your your TLB intensive data to come out of malloc and your IO intensive data to sort of come out, or your network bottleneck data come out of SSDAlloc, you would not be seeing so many TLB misses. The TLB misses would be equal to the let's say the IOPS of the Memcache box itself, which most modern CPUs can actually handle fairly well. I'll come to the overhead of SSDAlloc in more detail. So here's an overview of how SSDAlloc works. Let's say you have a memory manager like malloc, in this case SSDAlloc. Let's say you create 64 objects of size 1 kilobyte each. Okay? What a traditional malloc memory manager would do is it would take 16 4 kilobyte pages, split it into 64 1 kilobyte objects and return these pointers to the application. What SSDAlloc does is it creates 64 different 4 kilobyte virtual memory pages and allocates these 64 pointers as these 1 kilobyte blobs of data to the application. The 3 kilobytes portion in each of these virtual memory pages is not utilized for allocation in future. So clearly, I mean, this frivolous use of virtual memory can lead to wastage of physical memory. So what we propose is we have a very small page buffer. We restrict the number of pages, the number of virtual memory pages that are in core at all point of time to be a very small quantity. Let's say 5% of your DRAM is actually all the virtual memory pages that are resident in core at all points of time. The remaining 95% or remaining large portion of DRAM is actually used as a compact object cache, where these objects that you are creating using this memory allocator are stored compactly using a custom hash table interface. And because the virtual memory system tells you which pages are being modified, you know precisely which objects are being modified, which means that you can implement the SSD, use the SSD as a lock structured object store. Now that's the rationale behind, this is how the SSDAlloc system works. So to implement this system, what we did was all the virtual memory that is allocated to the application is protected by IMProtect. And when the application tries to access any of this data, it takes a fault. In the fault handler, we figure out where the object is. It's either currently in the RAM object cache or on the SSD. If it's in RAM object cache, we manufacture the virtual memory page immediately and return the control back to the application in the fault handler. And if it's not, we fetch it from the SSD, cache it in RAM object cache, manufacture a page and put it in page buffer and return the control back to the application. So coming back to Andrew's question, this is the overhead in SSDAlloc. So we took a 2.4 gigahertz quad core CPU. It had 8 MB of L2 cache, just for a TLB miss. So this is not a miss that goes to DRAM, but just for the hardware to figure out that this is a TLB miss, it takes about 14 nanoseconds. And address translation for SSDAlloc, which translates virtual memory addresses into SSD locations, that's about 46 nanoseconds. Page materialization, which is take a new physical memory page, copy the data from RAM object cache into this physical memory page, that takes about 138 nanoseconds. And the combined overhead of all this process of manufacturing a page on a fault is about 800 nanoseconds. And the bulk of the overhead is still NAND-Flash latency, which is about 300 to 100 microseconds. So if you're still bottlenecked, if your application performance is bottlenecked by the random IOPS of the NAND-Flash device, then you're not so much bottlenecked by TLB itself, because the NAND-Flash is probably doing somewhere between 300,000 to 400,000 or even a million IOPS per second. And in those cases, the TLB is not going to be the bottleneck. So here's a results overview. We modified 4 different systems: Memcache, a Boost template library based B+ tree, a packet cache, which essentially is caching Ethernet packets inside a network and trying to do network acceleration, and we also modified HashCache. The modifications required only 9 to 36 lines of code. Some of them were simple, find and replace, find malloc and replace it with SSDAlloc. But some of the systems are more complex. For example, Memcache, what it does is, instead of mallocing individual objects, it creates its own memory allocator. Each time it allocates a large 2 megabyte or even 5 megabyte portion and builds its own memory allocator. So to modify such systems, we needed more number of lines of code. So in terms of performance, SSDAlloc obtained up to 17 times more performance than unmodified Linux swap, and up to 4.5 times more performance over lock structured swap. So clearly Linux, the native Linux swap is not a good comparison point, because it it was not originally built for flash memory devices. It was originally built for disks, and in the disk world, once you started swapping, performance really did not matter. It was more like a like a barrier before killing an application. It was like a worst case performance sort of a thing. So that's why we modified the Linux swap to be lock structured, where it was storing the pages in a lock structured fashion. We also show this as a comparison point. And the reason why it performs 4.5 times better than modified Linux swap, which is lock structured swap, is because our writes are actually restricted to object sizes, as opposed to marking data dirty at a 4 KB granularity. We're marking data dirty at a object size granularity, which means your write sizes are much lower for random writes. And most of these systems that we modified are hash based systems, which means that writes are going to be randomized and reads are also going to be randomized. And because our writes are restricted to object sizes, and we actually cut off the size of the object at 128 bytes. So you might be wondering, for the one object per page model, not only TLB but your page tables are also going to be larger, right? So if you have let's say 2 byte objects or 5 byte objects, you don't want to create a page table entry for a 5 byte object. So what we do is we cut off object sizes at 128 bytes, and if you have an object requirement of less than 128 bytes, we create those objects from these 128 byte pages. So we build a coalescing allocator on top of these 128 byte pages, and for any object size that is less than 128 bytes, we create it from that memory allocator, which means that the smallest object size that you can have in SSDAlloc is 128 bytes. And if you have random writes, it means that it's going to write 32 times less data to the SSD, because in a standard virtual memory system, you're going to be marking data dirty at a 4 KB granularity. So here are some micro benchmarks to enhance to show the benefits of SSDAlloc. What we did is we took a 32 GB array of 128 byte objects, and we created these objects using SSDAlloc and malloc in unmodified Linux swap and also lock structured Linux swap. And we varied the number of reads and writes in the system. We started off with all reads, and then we went on till all writes. So if you look at the throughput per the number of requests per second that you have in terms of thousands of requests per second. These are normalized performance increases. If you look at how SSDAlloc performs over unmodified swap, the performance is anywhere between about 2.5 to 15 times, 14.5 times. That is, as the writes are increasing, the performance of SSDAlloc is much better. This is evident in terms of SSDAlloc requiring to write much lesser and also doing sequential writes as opposed to random writes that unmodified swap does. And if you look at the SSDAlloc's benefits over lock structured swap, the benefits are still in terms of having to write much lesser for random writes. This is because our writes are restricted to object sizes as opposed to 4 kilobyte pages. And we verified these results across 5 different SSD vendors in the paper. I encourage you to go and read the paper for a detailed set of results. And here are some benchmarks for Memcache. We took a 30 GB SSD and 4 GB of DRAM, and 4 Memcache clients were were essentially sending requests to this particular Memcache server. We modified the slab allocator of Memcache, as I said, to use SSDAlloc, and these are the performance results. As the x-axis is the average object size inside Memcache. As the average object size decreases, the performance of SSDAlloc increases. But if you look at the performance of SSD swap and SSD lock structured swap, the performance does not actually depend on the object sizes, because regardless of what the object size is, they're marking a page as the entire 4 kilobyte page as dirty, and they would still be reading an entire 4 kilobyte page from the SSD whenever an object is required. And this is for a random workload like Memcache. So here's some of the current work that is going on that I've been doing, trying to optimize SSDAlloc. The first thing that we are working on is rethinking virtual memory management itself. In SSDAlloc, obviously there is this problem of 95% of your physical memory is available only after a fault. And if your working set size is so and so that the working set size can actually fit in DRAM, this is clearly a nuisance. So for this purpose, what we do is we still want to maintain this one object per page semantic, but we don't want the overhead of having to take fault for accessing a huge portion of your DRAM. So what we do is the following. What we do is we create sparsely mapped virtual memory pages. Let's take these 4 virtual memory pages. Each of them are actually sparsely mapped. The first one is mapped at to the application in the first kilobyte, the second one is mapped in the second one, and the fourth one is mapped in the fourth one. Now these virtual memory pages are actually mapped to the application in non-interleaving portions, which means that by using some page table magic, they can actually share an underlying physical memory page, which means that you're still going to get the advantage of detecting reads and writes at an object granularity, but you'll still be able to pack all your physical memory using useful objects without actually having any page faults.
On the top, you've got a virtual memory page, but you're not using all of that page, you're only using part of it.
Right, and the usage is determined at malloc time. So when the application calls for malloc of 1 kilobyte, I'm gonna give him 1 kilobyte. And the contract between the malloc user and the malloc implementer is that you're not gonna use the data beyond these 2 pointers.
So they're not overlapping, so that when it maps down to the physical page, they all sort of fall into place.
Right.
In JSON on the physical page.
So this still gives you pages which are smaller than 4 kilobytes, which means that you can do all the SSD optimizations you want, but your DRAM is still not wasted. So whenever these sparsely mapped virtual memory pages are in core, they're going to be sharing physical memory. So that's the advantage. So that's the first work that is ongoing work. And the second ongoing work is trying to do more virtual memory centric tiering. So what happens in traditional operating systems is that you don't have a reverse pointer from physical memory page to the virtual memory page. So traditional operating systems, what they do when they have to select a candidate for paging out is that they have some sort of usage information, statistics, on a physical memory basis. They don't have a virtual memory usage basis. So when they have to page out a page, they need to go to each individual process, scan through their virtual memory regions, and see which of these pages has not been recently used. Now, when they find such a page, they page it out. So this is a CPU intensive process of there's a scanning of all these virtual memory pages that is going on. So in Team, what we did is we try to make it more virtual memory centric. We maintain virtual memory page usage statistics. So for all the virtual memory pages across all the processes, we maintain statistics, clean statistics, and these statistics are actually used. And this reduces the CPU requirement of implementing page replacement policies inside operating systems. And the second optimization we have done as part of Team, which is Team stands for Transparent Expansion of Application Memory, by the way. The second optimization we have done in Team is that virtual memory page tables are already translating some sort of address. They're translating virtual memory addresses to physical memory addresses. And flash memory FTLs also do some sort of translation. They translate logical block addresses to physical block addresses. So there's 2 levels of indirection that is going on in these systems where you would like to use flash memory devices as virtual memory via virtual memory. So we try to reduce this overhead, and we implemented an FTL fully using virtual memory page tables and as a sparse FTL. And that's the second part of the work. There's a third thing that we are trying to do, where we're trying to introduce some amount of flash memory inside a cluster, and it's more like the cluster is actually implementing a block device. The block device comes from the cluster, and we are trying to do some sort of custom tiering within the cluster. So what we're trying to do is, let's say you have a block that is cached in DRAM on a particular machine, and there's also a block that is cached in DRAM. The same block is actually cached on a DRAM of a different machine. Now, if these 2 systems are not talking to each other, they might make suboptimal decisions of how to implement page replacement policies. So we're trying to see if page replacement can be done on a cluster basis, where these systems are actually communicating with each other with respect to access frequencies, and they're doing some sort of collaborative tiering, so that you don't make these decisions independently from machine to machine. So that's some ongoing work, and this is some future work that I have. So there is some amount of work in maintaining page tables for multi-threaded systems which are using large amount of virtual memory. Now, because we are talking in terms of secondary faults, higher level faults, these multiple threads need to be able to modify page tables scalably. So there is some interesting work that can be done in lockless data structure type management of page tables inside operating systems. And there's also some work that we can do in terms of how to tier flash memory. Can look at 2 different models. One is the SAN model, and the other is the Hadoop model, and somewhere in between as well, where there are some nodes in the network which have more amount of flash memory than other nodes, which means that they have more appetite for data. And the third is in terms of reliability of transparent tiering system. If you have a transparent tiering system, if the data is corrupted in one layer, it will eventually be corrupted in all the layers, because the data will still needs to trickle down. So we need to try to figure out methods in which the transparent tiering systems are more reliable and more secure in terms of what kind of safety barriers you can provide in terms of managing your tier in the second level tier, the flash level tier. So here's a summary of the talk. HashCache is a DRAM efficient and seek optimized cache index with an LRU-like replacement policy. It's about 6 to 10 times more efficient than commercial systems, memory efficient, and 20 to 50 times more memory efficient than open source systems. It enables large disks with only netbook class machines. And SSDAlloc is a complementary technique which is useful for building such hash tables, where if the hash table size grows to much larger sizes, you can use SSD without actually having to modify your application. And the modifications are restricted to only the memory allocation portions of the code. And in most of the systems that we modified, it was only 6 to 30 lines of code. And the systems end up performing 3 to 15 times better than existing transparent ways of using flash memory as virtual memory devices. And they also, SSDAlloc also has the benefit of increasing the SSD life by up to 32 times. Now I'll take questions.
So you said that it performs a lot better than existing transparent techniques. Can you relate it to existing techniques that are SSD aware? Help us understand how it fits in.
Sure. So in terms of this, like I have this example. So let's say you are implementing a Bloom filter. Now, one way you could implement a Bloom filter is take an existing Bloom filter library that was built for DRAM and use it as a swap device, right? And the second thing you could do is, instead of doing these random writes in your Bloom filter at a 4 KB granularity, you can do it at a much smaller granularity using something like SSDAlloc, right? This is clearly beneficial, but in terms of SSDAlloc is clearly not aware of what the application is trying to do. So if the application developer is aware of a better data structure which supports this sort of a thing, you can not only implement the data structure using this interface, but also the native storage interface. Now we propose using virtual memory as the interface for flash memory only because if you look at new memory technologies like phase change memory and other memristor sort of technologies, going forward, I mean, these technologies are growing lower in latency, so it makes more sense to build these systems to use as a memory as opposed to using it as storage. So this is a complementary technique. So this enables usage of flash memory on a wide variety of systems, but data structures are really still important. If your application developer can build a smart flash-aware data structure, you have to do it.
That makes sense. Can you give me an idea of, I mean, are flash-aware data structures going to perform many orders of magnitude better than the transparent things, or just, I mean, in other words, have you gotten most of the benefit, or have you gotten only a fraction of the benefit you can get by, because if the core of an application is 1 or 2 data structures that can be rewritten, that can buy you additional orders of magnitude again, then transparency is nice, but really, when you're all done, you're going to want to actually use the custom data structure.
Right. So this is still the reason why, I mean, a lot of people will spend a lot of effort in going and building, the cache line aware software. I mean, even in a purely DRAM world, you would want to modify your data structure so that your caches are being used appropriately. So in terms of building a data structure appropriate for the underlying memory technology, those sort of techniques will still be important. So coming back to the Bloom filter example.
There are additional orders of magnitude there?
So coming back to this Bloom filter example, so you could build the Bloom filter in a regular way for using small page sizes, or you could build the Bloom filter such that all your K functions actually reside in the same block, right? You could do some additional randomization to make sure that all your K random functions needed for the Bloom filter are on the same block. Now this actually readily gives you K times performance improvement, right? So depending on what the K inside your Bloom filter is, you'll get such a benefit. So I guess, I mean, this makes flash memory useful in terms of memory, because building in-memory data structures is much easier than building on-disk data structures. So in terms of development, it's going to reduce your overhead, but performance will still heavily depend on the kind of data structure you're building and how flash-aware it still is.
It seems like most of the complexity in SSDAlloc comes from the fact that you want to support existing unmodified code to the extent that somebody calls an allocator, gets back a pointer, and at any point in time in the future they can just go and fiddle with the state that thing points to.
Right.
And so that means you need to track updates through the virtual memory system and all this kind of stuff. And so 2 questions I have are, one, am I correct in thinking that this is strictly worse than a system in which you have like an explicit access this object and I get a copy of it, now save this object?
Mm-hmm.
have you considered whether an API like that, like how, I'm thinking that it would not be very hard either through compiler transformations or manual code rewriting or a little bit of hacking to take some existing data structure and modify it to insert these calls to say, require release. For example, you could do that when you require and release locks perhaps, or you could use TM techniques, or you could do a little bit of magic that would make a lot of the overhead of doing it completely a virtual memory system go away.
Right. So definitely, so in terms of what semantics that the programming language has, there are multiple optimizations you can do. One is, let's say you have some sort of transactional semantics, then you can completely get away with your RAM object cache and this the other requirement. If at the beginning of, let's say, a function call, in the function call you declare these are the set of objects I'm going to be using, or let's say you acquire locks, the handle still could be virtual memory, but but it'll get away from some of the overhead that SSDAlloc has. So in trying to be completely transparent, yes, we definitely had to go jump through a lot of hoops, but in trying to be less transparent, I mean it's sort of a trade-off. So you either want to use custom object handlers, or you want to be transparent to existing applications which have used virtual memory, and then try to make their life easier.
I guess my question is similar to John's, which is, do you have any sense in the spectrum of achievable performance where these different trade-offs sit?
Right. So we did a spec benchmark sort of with SSDAlloc, and we also did a spec benchmark with the Chameleon system I was talking about, where all the physical memory is actually accessible using just virtual memory pointers. And so in that case, we actually saw a performance increase of about 16 times. And this is a purely in-memory benchmark. It does not use the SSD at all. And by using SSDAlloc-like technique, where you're taking fault to actually access, let's say, 95% of your DRAM, that was actually causing the problem.
But I guess my question was different, which was, if you were using the SSD, what's the overhead of using it in the completely optimal handwritten data structure versus using it if you're prepared to tweak your object access routines versus this?
So
how do those things?
So one pathological example that I gave, that I just gave, was the Bloom filter example. There are these flash-aware Bloom filters. What they do is all their k-hash functions actually fit into the same block. They use additional randomization for this. And if you use a regular Bloom filter, which is not flash-aware or which is just built originally for DRAM, what you could the k random writes could actually translate to k SSD random writes. So there you readily see a k times performance improvement, not only in terms of number of writes but also in number of reads. So these sort of examples are certainly there. So in terms of what is the right thing to do, build a flash-aware data structure, and what is the right interface. People are fairly familiar with memory sort of building. I mean, they find it more convenient to build in-memory data structures as opposed to building storage-like data structures. So that's the reason why we propose this interface moving forward with new non-volatile memory technologies.
In the SSDAlloc part of the talk, you mentioned different vendors. And in the other market, we do see a wide variety of different devices.
Right.
With very different performance characteristics. And your work tried to integrate SSD into virtual memory system. Probably it's not many of the vendors are considered. We're just basically wondering, how the performance differentiation goes like across vendor systems.
Sure. So there are some flash memory devices which actually do more random writes than random reads. This is because they are bottlenecked by SATA, and then if you're doing a lot of random writes, they're still doing a lot of sequential writes onto the SSD. And for these sort of cases, because they have a fully associative FTL, so the performance essentially boils down to the kind of FTL that they have. So if your FTL is not optimized for random writes, the performance would be very high with SSDAlloc. But if your FTL is actually fully mapped and can do random writes really well, the performance benefits will boil down to the object sizes. Let's say your object size is 512 bytes, and the virtual memory system is actually mapping at 4 kilobyte range, 4 kilobyte dirty. Then in the SSDAlloc case, you'd still be writing 8 times less data. So even in those cases, you get the benefit. So regardless of what the FTL looks like, you end up getting benefits from the SSDAlloc model.
Another question for the SSDAlloc. how much is additional, basically, in-memory data structure you need to maintain, basically to consider this fragmented object?
Right. So
Basically, table to map it.
Right. So the page table overhead for SSDAlloc, so the virtual memory to actual SSD locations that you have. So for the page tables, yes, I mean each page table entry is probably 8 bytes in size for 64-bit systems, and in those cases, the data structures of the page table data structure of SSDAlloc are themselves pageable. So the page tables can actually reside on the SSD itself. So if you have like traditional virtual memory systems, if you have a four level page translation mechanism, then many of these pages required for representing the page table itself can reside on the SSD itself. So depending on the working set size, if your working set size is small enough that it fits in DRAM, then you wouldn't see much of an overhead in terms of page table, the overhead of storing these mappings in DRAM, because if the working set size is small, hopefully the page tables themselves will fit in DRAM for the current working set.
So in the beginning you mentioned, right now we have very large SSDs, for example, 10 terabyte SSD from HashCache, right?
Right.
If you are actually basically mapping such a large VM space, what is the data structure size, and how much is the
So with the current version of the Fusion IO FTL, a 10 terabyte hard drive would have about 32 gigabytes of FTL requirement. And the current Fusion hard drives actually don't have a pageable FTL, which means that all this 32 gigs is going to be DRAM. So I think this summer or by the end of this year, they're coming up with an FTL which actually resides on the SSD. And only the mappings that are currently being used by the application or by the OS are actually stored in DRAM, and the rest of the mappings reside on the SSD. So yes, moving forward, if you want larger flash memory devices, you need to think about mapping overhead. And mapping overhead can be done, and as I mentioned in one of the team systems, is by not storing page table mappings and also FTL mappings, trying to combine them. That is one sort of optimization you could do to reduce mapping overhead. The second optimization you could do is make the mapping data structures themselves pageable, so that you do demand fetching of the mappings itself.
How long is the typical SSD lifetime?
So if you look at the Fusion IO drive, it's an 80 gig hard drive. It's rated for 5 petabytes of writes, and as the latency goes further down, what ends up happening is, these companies would like to give you warranty for 3 years, but as you go to higher capacity, the number of erases that you can do on these devices is decreasing. So right now they're at a point where 5 petabytes is actually not enough for 3 years if you're doing writes 24/7. But there are not many applications, fortunately, which are doing writes 24/7. If you look at more realistic applications from the logs from a data center of their customers, they can still last 5 years on the shelf. But I guess once they move to 2x nanometer devices, they're going to have this problem of using these MLC devices, which are rated only for 5,000 cycles. So what they're doing is, so instead of giving you purely SLC devices, what the flash vendors are doing is they're taking MLC devices, which are, so if you look at, let's say if you want 100 gigs of SLC, and if you take 100 gigs of MLC, you would think that the price of the MLC is certainly cheaper. But what ends up happening is the economies of scale of MLC are different. So MLC is actually cheaper than SLC, not only in terms per byte, but not only twice per byte, but actually much lower than that. So what these companies are doing is that instead of buying SLC, they're buying MLC and using the MLC as SLC. So they're not using the two levels inside MLC devices. So that actually gives them slightly higher number of write cycles as well. And so when they go to 2x nanometer, instead of getting that really low number of 5,000, they'll be getting something like 8,000. So maybe for the next 4 or 5 years, they can still maintain this saying that you can write 5 petabytes, but it'll still last for 5 years, sort of a number.
One quick question. I'm wondering if thought about SSDAlloc in managed languages, where you might both be able to track object use without going down to the VM, but also not require any changes up the language.
Right. So what we can do is take something like JVM, go modify JVM to use something like SSDAlloc, and then you readily have best of both the worlds. The JVM itself is using the SSD in an object-oriented fashion, and you also have this benefit of being able to translate pointers independently without having to change things for the application. So you can definitely do that, and instead of going this route, what you can do is you can go modify the JVM itself to be flash aware. So instead of because they are all custom pointers, and you also have an indirection table within the JVM itself, which is mapping the Java pointer to a particular virtual memory pointer, let's say. Those can be transparently modified as well. So we tried doing this inside JVM, and we essentially went inside JVM, replaced mallocs with SSDAllocs, and tried to see what happens. And it was not so straightforward. JVM also is a coalescing memory allocator. It creates large 5 megabyte portions and then splits those into objects and those. So it was much more complex than that.
Okay, thanks, speaker.